Okay, so we're going to begin question 11 the way we start any other question, and that's going to be to first draw a picture of what's going on spatially, label our points, and then list out our information as neatly as we can for each of the two runners, and then take it from there in terms of what approach we want to use to actually solve the problem. So the first thing we're going to do is draw that picture. And what we have is a race which starts at x equals 0 and it ends at x equals 8 kilometers. Runner 2 is going to complete this first, so this x in space, this position in space, we'll say this is x final for runner 2 because runner 2 is the one that's running faster. This x initial here is going to be the same for both runners 1 and 2. When runner 2 is at the finish line, runner 1 is going to be somewhere behind him. So this is going to be x final for runner number 1. Now in this problem, we're looking for this distance right here, which we'll call delta x. And delta x is equal to x final 2 minus x final 1. And this is a relationship that you have to come up with on your own. This one's pretty straightforward, but you still have to come up with it on your own. Okay, so let's identify our information for each of the runners. So we have runner 1 is the slow runner, and x initial for the slow runner is 0. X final for the slow runner is an unknown quantity. The velocity of the slow runner is 11 kilometers per hour, and the time it takes is also an unknown quantity, but we know it's going to be equal to the time for runner 2. Runner 2, the initial position is 0. The final position is at 8 kilometers. The velocity of runner 2 is equal to 14 kilometers per hour, and the time it takes is unknown. Okay, so before we get started, typically when we solve problems in physics, we're going to stick with MKS units, where M is for meters, K is for kilograms, and S is for seconds. This is going to be the SI units that we use all year long. And that's important that we are constantly sticking with meters, kilograms, and seconds, because if you were to use kilometers, grams, hours, then that can create problems, especially whenever we have to include constants, physical constants, in our calculations. For example, the constant little g has units of meters per second squared. It also has units of newtons per kilogram. So you can see that if you were to try to do things in centimeters or kilometers and hours, that this constant is not going to work properly in the equation. The constant capital G has units of newton meters squared per kilogram squared. And so again, if we're using kilometers or grams or pounds for force or something like that, then it's going to create problems for us. So we always want to make sure that we're using meters, kilograms, and seconds. Now, that being said, there are exceptions to that. And if you don't know what the exceptions are, then you must go back to meters, kilograms, seconds. You can never go wrong by doing that, by using meters, kilograms, seconds. But this happens to be one of those exceptional problems because we don't have any constants and we're not mixing our units. So if we were to ever calculate a time, the time would be in hours because the units of velocity are kilometers per hour. When we calculate positions, then the position is going to be in kilometers instead of meters. So this is one of those exceptional problems. Now, a common way for solving problems, especially problems in kinematics, is to use graphs. So if we construct a position time graph for this particular problem, then what we see is that the fast runner creates a graph that looks like this. The slow runner creates a graph that looks like this. And if we say that 8 kilometers is right here along that line, then the fast runner, this is runner 2, the fast runner obviously reaches it first, and then the slow runner reaches it second. And what we're looking for in this problem, which this of course is not drawn to scale, but what we're looking for in this problem is basically what's the distance between these two lines at this time right here, at this time t2. We want to know what is that distance between those two lines. So we've got the distance between this point and this point. This becomes x, we'll say x final 2, this is x final 1, and what is that distance right there? So using the graphical approach is not particularly helpful for us in this situation. Absolutely, it could be used. It may provide wonderful insights for you, help you to understand the problem, and definitely you should be drawing position time graphs for pretty much all of your problems. It just helps you to better understand what's going on from multiple perspectives. It gives you a more complete picture. So the graphs are really important. Okay, so we're not going to use the graphical approach in solving this problem because we've drawn our picture. We can see that it's not particularly useful. Even the velocity time graph is not particularly useful unless we were to find T2 in the problem, and then that makes it a little bit more manageable. But again, we're calculating something else. So if we're going to go through the process of calculating, it's going to be just as easy to do it with algebra. So in order to set up this graph, we need to know actually what the equation of each of these lines are. Okay, and that's where the algebra part of your problem starts as well. So let's set up those equations. For runner 1, there's actually both runners, there's only ever one equation we're going to use, and that's going to be d is equal to vt, because this is constant motion. So d1 is equal to v1 times t1, and d2 is equal to v2 times t2. Okay, so these are the equations that you use to set up your position time graph. Now, we are looking for positions. X is a position. All right, so we're looking for positions, so we got to write this as delta x1 is equal to v1 t1, and delta x2 is equal to v2 times t2. Now, this becomes x final 1 minus x initial 1 is equal to v1 t1, and x final 2 minus x initial 2 is equal to v2 times t2. We know that the initial velocity is 0, so that enables us to get rid of x initial for each term. And we're left with x final 1 is equal to v1 t1, and x final 2 is equal to v2 times t2. Now, where this is all really important in terms of rewriting displacement as delta x, or x final minus x initial, is if, suppose, we were talking about, referencing some other point in space. Maybe this is home, right? And maybe the two runners started where x was equal to 3 kilometers, right? And home was equal to x equals 0. Then it's essential that you set it up using positions, because x initial is no longer 0. Okay, so anyways, so these are the two equations that you're going to use to make a position time graph. And from here, we want to actually solve our problem now. So how do we even go about doing this? Well, it might seem like common sense, and what I'm telling you is like, yeah, duh, right? But here's the thing. I've seen it time and again where students they don't know where to start, and they just kind of pick any old starting point. They just find an equation on the equation sheet and then they go with it. Or maybe they'll just take the equation from runner 1 and they'll start there, the equation from runner 2, and they'll start there. Here's the problem with that. We're looking for, if you recall, we're looking for that distance delta x. Delta x doesn't show up in either one of these equations. Now, we had a delta x here and a delta x here, but that's not the same delta x as this. These delta x's were this, right? That was delta x2. I'm sorry, 1. That was delta x1. Delta x2 went from 0 to 8. So this is a totally different delta x. So that's where it's important that you write out these relationships, because the basic strategy for problem solving is always going to be to start with an equation that gives you what you're looking for, that grounds your problem. And basically all you have to do is take one blank at a time, one unknown at a time, and fill it in. Find a way to get a value for it, or find a way to put it in terms of the variables that we know. So that's what we're going to do here. So what we have is this. We're going to start with this equation, delta x equals x final 2 minus x final 1. And for simplicity, I'm just going to write it as x2 and x1, with the idea that they're the final positions. So we're going to start with d is equal to x2 minus x1. Now, x2, we already have a value for that. And so I'm just going to leave that as x2. There's no need to rewrite that. And x1 is equal to v1 times t1. But we know that v1 or t1 and t2 are the same, right? We know t1 and t2 are the same. And so what we're going to do is, off to the side, we're going to determine t1 by using information for runner 2. Okay? So how do we do that? Well, runner 2, his motion is modeled by x2 is equal to v2 times t2. So t2 is just x2 over v2. So we write d is equal to x2 minus v1 times x2 over v2, or d is equal to x2 minus v1 over v2 times x2. Now, I did that for a reason, because I wanted you to see that in terms of a unit analysis, we have length units on the left side of our equation, and on the right side we have a unit of length for x2, and and then we have a unit of length here, and then when we look at the ratio of v1 and v2, there are no units. So dimensionally it works out to the correct units. That tells us our algebra is at least close. Finally, this ratio of v1 over v2, it's just giving us, if you look at all the math here, the math is telling us that there's going to be a percentage of whatever x2 was is x1. That's what it's telling us. x1 is only going to run maybe 70% of x2 because of the speed. All right, and so ultimately what we get here is, let's see here, d is equal to 8 minus 11 over 14 times 8. So let's go ahead and calculate that. So we have 8 minus 11 divided by 14 times 8. And that's going to be equal to 1.71 kilometers.